by a quick show of hands, how many people have taken an undergraduate level or graduate level course in that has at least touched upon linear regression? Okay, so a little over half. A little over half. About how many of you people have experience applying linear regression on your own problem or on work-related problems? Okay, it's slightly less. Okay, great. So for those of you who have experience applying linear regression, as you know, it's a huge, huge topic. You could take multiple graduate level courses easily just on linear regression. There's a lot of depth here. So as I'm going through something, if there's something that you have to add, feel free to interject and contribute to this conversation as well. All right, so our agenda for going over linear regression is that we're going to talk about the form of linear regression, how to interpret that, how to interpret some of the output of linear regression, and how to transform variables using some common transformations that I see a lot when dealing with linear regression. And then we're going to talk a little bit about some of the inferential nature of linear regression, some of the assumptions that go into linear regression. And the majority of our time today is going to be going through code examples. The package we're going to be using today is a package, the scikit-learn package. We're using the scikit-learn package because it has functionality for almost everything that we're going to be covering in class, and so we want to have some continuity there, and that's the package we're recommending you defer to for your own personal projects. But that being said, there's another package out there called stats models, which I'll also be covering in class today. And the stats model package has some additional information that is useful when running linear regressions. So where does linear regression fall in this chart of continuous versus categorical response, if any, and whether it's supervised or unsupervised machine learning? What's that, Barry? Continuous unsupervised. Any other thoughts? Continuous supervised. Yes, so the linear regression actually is a continuous supervised method. It's supervised in the sense that we have a continuous response that we're trying to predict, and we can use that continuous response that we're trying to predict to evaluate the quality of our model's ability to fit the data. What is the motivation for learning linear regression? Actually, I'm curious, for those of you who've done it on the job, in what context have you used linear regression, and what have you used it to predict or make inferences about? Yeah?
Forecasting.
Forecasting?
Forecasting building permit revenue.
Okay.
For a municipal government.
Okay. Gotcha. Yep.
I went to a conference in Miami where, if you heard Glassdoor, it's the one that tells you like the salaries of different companies.
Yeah.
What they were doing was they were looking at cities that don't have a specific job title, like the example they use data scientist in Miami, because there are none in Glassdoor. So they use the regression to try to figure out what would the salary of a data scientist in Miami be based on demographic variables.
Yeah.
So that was cool.
Yeah, I've seen linear regression used commonly as an interpolation technique or imputation technique. Yeah. Yes, it's a very widely used model, and that's part of the reason we go over it in the class, because it is so popular. One of the reasons why it's so popular is because it's a very fast algorithm. As we'll see if we have time today, going through some of the linear algebra that's behind the actual algorithm, it's a relatively simple and straightforward algorithm. So it's very fast, so you can use it on large data sets. It's relatively easy to use out of the box in the sense that it doesn't require a lot of these tuning parameters that we've talked about. It can be harder to use if you're trying to be really confident in the inferences you're making based off the model. But if you're using this in a sort of machine learning approach and just trying to make predictions and evaluate the quality of those predictions, you don't have to do a lot of fiddling with the tuning parameters to evaluate that. I think the biggest reason that it's so popular, or one of the biggest reasons, is that it's very interpretable. You get an output that gives you statements about the relationships, the strength of the relationships, the significance of the relationships between input explanatory variables and output variables. And then it's the basis for other methods that you'll see very commonly. So what is a regression model? This definition says a functional relationship between input and response variables. The simple linear regression model, which is what we're going to start with, captures the linear relationship between a single input variable x and a single response variable y. and it takes the following form. And this is a simple linear regression. So you have your y, which is your response variable, an intercept term, a coefficient value for your input variable, and an error term. And so let's go through each of these real quickly. So y is the response variable, the variable we want to predict. X is the input variable, so this could be the unemployment rate in a particular location and the salary of a data scientist, or your example, I think, was the price of a government permit.
Revenue generated.
The revenue generated from government permits, and maybe aspects of the economy would be different input variables. The beta not value, graphically, geometrically, is the intercept where the line of best fit crosses the y-axis. Beta 1 is the regression coefficient, which determines, which states the strength of the relationship between the input variable and the output variable. And then whenever you do a regression model, you'll always have some kind of noise, some kind of unexplained variance, and that's referred to often just as a residual or as the error in the model. So graphically, this is what the simple linear regression is. You see the y-axis, the x-axis, the y being the variable you're trying to predict, and you see the beta naught value being, you see the line of best fit that best approximates the relationship between these two variables. You see the beta 1 value is just the slope of this line. For those of you who know calculus, it's just the derivative. That's all the beta 1 value is. And the beta 1 value is what tells you what the relationship is between your input and your output variable. And then the beta naught value is your intercept. And then it's not drawn here, but the residual is just the summation of the difference between each of these individual data points and the actual line of best fit. So any questions about that? Just the basic form, basic interpretation of the different aspects of the equation. Okay? So that was simple linear regression. Multiple linear regression is just an extension of simple linear regression to more than one input variable. That's just the difference in the terms there. Simple, one input variable, multiple, more than one input variable. A lot of times when you read textbooks, they'll show you a derivation for the coefficient in a simple regression case, and then if you want to find the derivation for the multiple regression, it will involve linear algebra, matrix algebra. So this is the form for multiple regression where you just have more x variables and more beta values. Okay. So the basic form is that, or the basic assumption, there are several assumptions that go into linear regression, but the basic assumption is that your relationship between your input variable and your output variable, or your input variables and your output variables, can be approximated using a line. You can approximate the relationship between these variables as a linear relationship. Okay? So how does one, what are the questions that one might ask when applying a linear regression? There's a lot of different questions, and we're going to go over an example. But one of the big questions is just, what is the impact of a particular variable on our response variable? Okay? And so to answer that question, we derive the coefficient estimates. And a lot of textbooks tend to use different notation to describe things, but one common notation that I've seen is just a hat. When you see the value in the hat, that's referred to as the estimate, the beta estimate. Okay? So what is meant by estimate? Well, this sort of goes back to a point that Sanam was talking about. Oftentimes when we're doing these problems, we have the sample, and we're trying to make an inference about the population. And so when we say beta hat, we're talking about the value, the relationship that we see given the sample of data that we're analyzing. Okay? So you could imagine having a population where you have a relationship between x and y, and you pull samples. Each time you pull a sample, you fit a linear regression, and you get a beta value. And each time, let's say this red line represents the true model, the true line of best fit for all of the data points. But we don't have all of the data points. We just have a sample of the data points. And so what we're likely to see is, as long as we're taking a representative sample, what we're likely to see is beta values that are similar to the true model, but they're not exactly the same, because it's not everything. We're just measuring a subset of it. So that's what's meant. This is a graphical description of what's meant by a beta estimate. Okay? Any questions about that? Pretty straightforward? Okay. And then one of the big parts of where you sort of get off into a lot of the statistics is just understanding how much confidence can I place in the results that are derived from the linear regression. And we'll go into some of that today. So how is, I just sort of glossed over, you have a line that is the best linear relationship between an x variable and a y variable. But how is this line actually defined mathematically? Mathematically, it's the line that minimizes the sum of squared residuals, and a residual is just the error term. So what does that actually mean? So for any given line that is attempting to approximate the relationship, you will have an error for each data point. And the error is just the y distance for that particular x point between the predicted value, the value that the line or the estimate is predicting, and the actual value. And so each of these terms is a residual. And then we square those residuals because we just want to know generally how much it's off. And summing this square of residuals is the function, the objective function that we're trying to minimize. And so conceptually, it's pretty, just looking at a two-dimensional space, it's just, you can see that this is a better line that fits this particular set of data than a line that was angled, up or down. So that's what it's doing on a conceptual level. The formula that you'll see for sum of squared residuals is usually something along these lines here. So you have, this is the error term for a particular data point. Y hat, again, is the estimated value. So that's the point on the line that corresponds to that particular x value, the data point. And so the y hat is the predicted value, and then the y actual is the observed value. And then summing, squaring each of those error terms and summing them up together gives you the sum of squared residuals. And this is the objective function you're trying to minimize. Now, to actually derive the coefficients, it's actually a fairly straightforward derivation. It involves some calculus, but if you have a calculus background, you can look it up. I could share it with you as well, and it's a fairly straightforward calculation. But it's just the beta values are just derived by taking the partial derivatives, setting them equal to 0, and then solving for the beta values. When it's simple linear regression, you don't have to use matrix math, but when it gets into multiple linear regression, then you do have to use the matrix math. After doing the calculus, this is the output equation, the matrix equation that is good for simple linear regression, multiple linear regression, and these capital letters represent matrices. Okay, the X just represents the matrix of X values. Just as sort of we've always been representing X values. Your rows are your observations. Your columns are your variables. And then the Y is just your response variable. So it's just a single, it's a bunch of observations, just a single column. When I first saw this, I was like, that doesn't really, that's interesting, but I didn't really get the intuition behind it. For me, what helps me understand this from an intuitive perspective is that if you think of the equation of a line and just trying to get the slope of the line, you could think of it as y divided by x. Well, when you do matrix algebra, you can't divide through by a matrix. But here we have the inverse of the matrix. This is sort of very conceptual hand-wavy, but you could think of it as y times x over x times x, which is loosely equivalent to y over x. So I don't know if that's helpful, but that's a way that helps me remember this particular form. And then the transposes are due to just matrix algebra. So T stands for transpose, and transposing a matrix just means transposing the rows and making them columns, and the columns and making them rows. So pivoting the data. Make sense? And I can show you.
So the negative one's 1 over.
Well, you can't divide through by a matrix, so it's not exactly 1 over. It's the inverse. It's subtly different. Yes.
Can you refresh my memory? The inverse of a matrix. What is that? It's the transpose you described. It's just rows, columns, rows. But the inverse is it? What is that?
So taking the inverse of the matrix is relatively straightforward for like a 2 by 2 matrix. I can just share the rule with you. It's a little bit more complicated for a larger matrix, and I'll actually show you what exactly this is doing. I have an example that I prepared in just a minute. It's not really going to say something.
Just so the inverse in general, so B is the inverse of A if A times B equals 1.
Oh, yeah, okay.
Or in the matrix activity. So when you're saying 1 over, for the integers, what is the inverse of 2? Well, it's 1/2, because if you multiply them together, you get 1. So when we think integers or numbers, rather, the inverse of a number is 1 over that number. But in general, the inverse of anything is a number or an object such that when you multiply them, you get 1. And as for numbers, it happens to be 1 over that number. But in matrices, it's just another matrix such that when you multiply them together, you get the identity matrix. The identity matrix being all zeros except ones in the diagonal. And the way to calculate them, sure, math computers will do it. But it's just, in general, it's just the inverse of a matrix is just another matrix such that when you multiply them together, you get 1. Or the identity matrix. That's all that means. And just the easier thing about in numbers, well, what's the inverse of 7? It's 1/7, because you get. What's the inverse of pi? 1 over pi, because when you multiply them together, you get 1. And that's the definition of an inverse in general.
Yep. Thanks, Adam. All right, so we'll walk through a calculation really briefly that shows exactly step-by-step what this is doing. So let's say you have an x. Again, this is your input variable. There's also another column if you want to include an intercept term. As the result of this beta matrix will give you beta naught, beta 1, and however many beta values you have in your x matrix. And then y is just a column vector. So setting it up, we have x transpose x, and this is what that is. This is x transpose, just swapping the rows and columns, and here's x as is previously defined. And if you do this multiplication, you get the right-hand side. What does this actually mean? Well, you're taking these values, you're multiplying them pairwise by the column, you're adding them together, and you get this value. And you do that 4 times for each of the 4 combinations in the 2 by 2, or each combination, and you get a 2 by 2 matrix output. I won't linger on this too much because this is sort of down in the weeds a bit. But here is an example of when you take this result. So we just did x transpose x. Now, if we were to invert this matrix, here's what the result would be. Here's an example calculation for how I got this value here. And there's a simple rule for taking the inverse of a 2 by 2 matrix, but it's not as simple for other larger matrices. And then there's this other piece, x transpose times y, and so this first term is x transpose, which we saw before, and then the y vector, and then you get the resulting value. Putting it all together, you get a 2 by 1 vector which has both beta values. So I know I went through that fairly quickly, but any questions on that?
Go back to your original question.
This one?
I thought it was the one with word or be not.
Beta naught? Beta naught is going to be the first term.
Where, I thought you would find that in your what is beta not?
Oh, I'm sorry.
Yeah.
Beta naught is just the intercept here. Make sense? All right. So usually when I see linear regression, I see the intercept term. I suppose you don't have to include that term, but that is the typical form that you'll see it in. All right, so that was just a very brief introduction to the form of linear regression. Let's actually go and look at an example. So if you'll go ahead and open your code file 05_linear_regression. That contains all of the code we'll be going through today. And in this example, we're going to be looking at an advertising data set. You can see on lines 15 and 16. So this example was actually taken from and modified from an example in the Introduction to Statistical Learning. And so hopefully, if you want to get more into the details after the class is over, you'll have some continuity between this example that we're going over in class and additional information that the textbook provides. So this data set shows there's 5 variables in this data set. One, and it's basically this advertisement spending by market, as well as the corresponding sales by market. And I went ahead and added an additional variable called the region variable, just for the purpose of illustrating some of the points in class today. And again, these are just dollar values. I think they're maybe in the thousands or millions. And so here's the dollar spend on TV advertising, dollar spend on radio advertising, dollar spend on newspaper advertising, and the resulting sales by market, as well as the region of that particular market. Okay? So in this example, we're going to use TV, radio, newspaper, and region as input variables or features, and we're going to think of the sales as our response. So what are some of the questions that come to mind that you might be able to answer using a linear regression on this particular data set? Mm-hmm. Yep. Exactly. What is the relationship between these input variables and sales? Sure. That's one question. What other questions?
Which one of those variables has the greatest impact on sales?
Mm-hmm. Yep. So if you're a business decision maker, how do we allocate our money? Which should we invest more money in? What should we invest less money in?
Either one of those, but add by region.
Okay. Yep. So are there interactions between particular regions, you know, having different advertising strategies for different regions? Yeah. Exactly. So those are some questions. Another question we might be interested in is how effectively can we predict sales based off of our spend in these different categories? So those are some of the questions we'll be going through in the example. So go ahead and read in the data, and you can follow along. I'm going to split the data into train and test splits, and I'm going to convert the data back into its data frame format, just for convenience. Now what I'm going to do is I'm going to create scatter plots to explore some of the relationships that I think might be in the data. So first of all, I'm going to create a scatter plot that shows the relationship between radio spending and sales. And for this, something that I don't think we've covered in class yet is just the idea of creating subplots. So here you're going to see an example of how to create multiple plots on the same window. So here is the relationship between the radio spend and sales. It looks like there might be some kind of relationship there. Let's look at the newspaper spend against sales. Newspaper spending against sales, probably not. It doesn't seem like there's too much of a relationship there, at least by itself. Let's look at the TV spend against sales. Looks like there could be a linear relationship there. As you increase TV, sales also tend to increase. And let's look at the last one, the region against sales. Are some regions are getting more sales out of some regions than others? Yeah.
Can you make the text a little bigger?
Yeah.
I'm having trouble.
Yeah, definitely.
Also, a little clear. Yeah. Oh, Jesus.
How was that?
Just saying, back, what do you think?
Is it better?
Can you do that in the back?
All right.
Is it something good to set up in Spider to have it make it into a window when you make a graph? Because I was just supposed to console.
Are you using the IPython console?
Yes.
Okay, so I think the default setting is for the IPython console is to make it appear in line. There is a setting if you go to preferences. It's all just the toolbar symbol, and IPython console, graphics, and instead of going to automatic, I think it should be automatic to have it pop out. And if it's in line, then it'll just appear in your console.
Okay.
Also,
There's not going to be subplots in line.
I don't know. Can you do subplots in line in your IPython console, or do you have to make them?
Yeah, but then it doesn't each one.
Mine did it together. You just have to run it at the same time.
Oh, really?
Yeah.
Heather, try running all the code at the same time.
You can run it piecemeal.
Yeah.
It'll go one by one.
Uh-huh.
If you select all of them where it
Okay.
establishes the official plot, it should run it all together. But it's
Okay.
content.
Okay. That work for you, Heather? Okay. And are you good, Matthew?
I'm working on it.
Okay.
But good enough for now.
Okay. Okay. So we just plotted all these different variables. It doesn't look like, it looks like there's probably a relationship between TV spending and radio spending. It doesn't look like there's a strong relationship between newspaper spending and sales. And there does not appear to be a relationship, at least just looking at it this way, between the region that you're in and the sales you're in. These are just very simple pairwise relationships, and there could be a lot more complexity going on here, but that's an initial sort of exploration of the data. So let's go ahead and look at the linear regression output using the scikit-learn linear model. So what I'm going to do is I'm going to import the linear regression from the linear model package, and then I'm going to instantiate a linear regression just using the default settings. Then I'm going to run the fit method, and I'm going to pass into the fit method the input variable first and then the output variable. So here I have train radio as my input variable, and then I have train sales as my output variable. Now, you'll notice something here, that there's this NP new axis. And so let me just show you what this is. So here's train radio. And you see it's just the series that you would expect. And the shape is basically it's being treated as a one-dimensional one-dimensional data structure. So with this, if you try running it without the NumPy new axis, I actually was getting an error. So when I do this, it's not actually changing. It's not changing the actual data itself, but it's changing the data from a one-dimensional data structure to a two-dimensional data structure. And this is just part of the way that scikit-learn requires that X data. So then the sales is just the one-dimensional form. Scikit-learn works for that. So I'm going to go ahead and run the fit, and then I'm going to access the intercept and the coefficient as follows. So the intercept here is 9.4, and the coefficient is 0.187. And so what is the interpretation of what these values represent? So in the case of the coefficient, how would you interpret the coefficient value of 0.187 in this example?
Each dollar spending on radio correlates to a 0.187 increase, the 18.96 increase in sales.
Yes. Mm-hmm. Yep. And then you would scale it based on the scale. I think it's thousands of dollars. So this would be each as long as they're the same scale, correspond. And the intercept, what is the interpretation of the intercept value?
If there's no dollars spent, that's weird.
Yeah. Yep. Okay. So, to get comfortable with the syntax here, I'm going to have us do a quick exercise. And given these coefficient estimates that we just went through together, I want you to predict the sales for the minimum value of radio spending in the data set and predict the sales for the maximum radio spending value. And then I want you to create a scatter plot that shows the line connecting the predicted values from the minimum and maximum value over top of the initial data. Make sense? So just go ahead and work on it. You can work on it by yourself or work on it in your group. And let's take 5 to 10 minutes to go through that. All right, so bringing it back in. By now it looks like most of you got the answer. The way to get ymin and ymax is just by going back to the basic form of the linear regression, multiplying your x variables by the coefficient and adding the intercept value. So here you see that form for ymin and ymax, and then once you have ymin and ymax, it's plotting the straight line is just a matter of taking the x values and the y values, and you see the straight line there, and then the scatter plot is just a matter of running the same scatter plot as before. The reason I show that is because when you use this predict method on linear regression, all the predict method is doing is what we just did manually by hand. It's just taking the x values and multiplying them by the coefficients and adding intercept. That's all that's happening when you're making a prediction using the predict method on linear regression. Okay, so it's very straightforward. Nothing complicated going on behind the scenes here. And so you can see that my ymin and ymax values are the same as when I just run the predict function, and I'm predicting based off of the minimum and the maximum values, the same values that I did before. Okay.
As for the linear equations, the facts, and why we use the data map for regression, is it because of multiple datas potentially? Like why? I'm familiar with y equals mx plus b.
Mm-hmm.
Why do we use beta 1 for m? Because we could have multiple m's.
Yes. Yes. One is just for simple linear regression, or the first coefficient that you're deriving, and you can have more than that. But it's the same equation form, just the equation for a line. Yep. Any questions about this? Pretty straightforward. Okay.
I have one question.
Yeah.
For the SL object you created,
Mhm.
when you do that fit,
Yeah.
what are the parameters you pass in? You pass in radio, sales, or just the numpy new axis?
Yeah, so I just mentioned that briefly. It's obviously x and y is the syntax there. The only difference between this and this, practically speaking, is one's a one-dimensional data structure and one's a two-dimensional data structure. I'm honestly not sure why scikit-learn requires you to have a two-dimensional data structure that you pass to as the x variable, but that's just a requirement for the way that the scikit-learn implements linear regression.
And the y variable is just.
But it doesn't require for the y variable.
Series.
Yeah, yeah. But if you were to do, and we'll just do it in just a moment, if we do multiple linear regression, this part wouldn't be necessary. I'm honestly not sure why it requires it. It just sort of seems like one of the weird aspects of the syntax. Okay. So now let's evaluate our model for how well it predicts how well it fits the data, how it makes predictions. So for this, I'm actually, before running this code, I'm going to go back to the slides, and there's a presentation called Model Evaluation Metrics. I'll pull it up real quick, actually. So go to, within slides, Model Evaluation Metrics. And you'll remember from last class, we went over two categories of model evaluation metrics. We briefly mentioned evaluation metrics for regression techniques and classification techniques, but we didn't go over anything for regression techniques because we were covering logistic regression, which is a classification technique. and we talked about ROC, AUC. We talked about the confusion matrix, sensitivity and specificity. For this, and we didn't cover anything for regression. So what I wanted to cover briefly is the root mean squared error, which is the metric that I'm going to go over the syntax for in our example. So what is the root mean squared error? It's a metric used for evaluating the fit of regression problems. As I said, it's the square root of the mean of the squared errors. And so you can think of it as the sum of squared residuals that we talked about earlier, taking the mean of that after doing the sum of squared errors, and then taking the square root of that. Sounds sort of like a lot of steps. Might sound superfluous to you, but if you think about the sum of squared errors, that's just how well is our how far off are our data points from each other. The mean is just the mean. What's the average distance? But at this point, we've squared our errors. And remember, we squared our errors because we just wanted to see generally how far off it was. And if we were to add positives and negatives, they could cancel out. And so taking the square root, the root mean squared error, is so that we're having an error term that's on the same unit scale as what we're predicting, what we're measuring, and what we're evaluating. So the one part of this, so just to explain the terms, yi is just the observed y value, y hat is the estimated or predicted y value from the regression model, and the summation over n, the number of observations. Okay? Now, so first of all, any questions about the basic form?
You said you square root so that the number is comparable to what you're dealing with?
Yeah, you take the square roots, the units are comparable to what you're making predictions off, what you're measuring. So if your units are thousands of dollars, and you square that, then it's not going to be thousands of dollars anymore. But when you take the square root of it, then you're having an error term that's in thousands of dollars, the same units. Now, the one part about this that's sort of non-intuitive, at least for me when I first, was that it punishes larger errors. It punishes larger errors. Okay, so what does that mean? To look at that, I thought just two trivial examples. In example 1, we have, real values of 100, 50, and 30, and predicted values of 90, 60, and 40. So the error for each of these observations is going to be just 10. Okay? The sign doesn't matter because we're squared. So the root mean squared error is just 10 squared plus 10 squared plus 10 squared divided by 3 square root, and that is 10. So another example where you have the first value is predicted correctly, the second value is predicted correctly, but the third value is 30 points off. So if you were to look at just the absolute error, the total absolute error, you could say the absolute error here is 10, absolute error here is 10, absolute error here is 10. So over here is like the mean absolute error, this would just be 10, just the same as root mean squared error. And the absolute error here, or the mean absolute error here would also be 10, because you have 3 points, and you have an absolute error of 30. But the difference between root mean squared error is that you're taking the square of the error term before you're taking the mean. And so you have 0 squared plus 0 squared plus 30 squared. So here you had, 100 plus 100, 300 divided by 3, and then square root of 100. Here you have 30 squared, 900 divided by 300, square root of 300. You have square root of 100, square root of 300. So why does this matter? Well, it matters because the linear regression is sensitive to outliers. And so a couple of values that are outlying values will change the regression coefficients, even if it's only a couple of values. And so this is a popular evaluation metric because it punishes in a sense. It creates, compares this metric to the mean absolute error versus the root mean squared error. The order of operations punishes larger errors over smaller errors. Any questions about that?
Does that mean that that was worse, or is that just kind of like a...
Exactly. That would mean this model is worse than this model, according to this metric.
Because it's less consistent.
Because that is one big error, it's saying one big error is worse than 3 smaller errors.
But it's even more accurate, just not precise. Correctly predicted 2 of the 3. Right on, but had a larger gap, so therefore it's not as consistent.
So I wouldn't call it, you could say it's accurate loosely. When I refer to accuracy though, or it's not, when I refers to accuracy, we're talking about a classification problem, usually. The percentage of that are predicted accurately. This is just numbers for illustrative purposes, but all of these numbers are on a continuous, all these numbers are on a continuous scale.
Is the mean root squared error used, or do you just put this for inside the sigma? Is that used at all?
Well, so if you were to do, if you were to have the root here, well then it would be duplicative, because you would be taking the square and then you would be taking the square root.
Oh.
Yeah. That's essentially what that is essentially what you're doing when you're doing the mean absolute error. Okay. That is the mean absolute error.
Okay.
So when I first started studying this, I was like, what is the difference between mean squared error and mean absolute error? But there is a difference. It's sort of a subtle difference. But I think it's a relevant difference for the context of linear regression. Okay, should move on. So how do we do this in code? Let's go back to the code. So what we're going to do is we're going to make a bunch of predictions. You see that on my console on line 80. And then we're going to import mean squared error, which is from the metrics package in scikit-learn. And I'm going to do mean squared error, and it takes 2 inputs, the observed values and the predicted values, but the order won't matter here. And this returns the mean squared error. What I want is the root mean squared error. So I'm wrapping that around the square root function from NumPy, square root. And so you see a root mean squared error of 3.82. Okay? One thing I didn't mention is I'm making these predictions and I'm assessing the model based off the test set. Okay? Now we can also take this a step further and we can go to we can use the cross-validation. And so for cross-validation, it's from a package called cross-validation. It's just cross-val score, and we went over this last class. But just a reminder, cross-val score takes the modeling technique that you're going to use to fit the data. It takes the input and output data. It takes the number of cross-folds that you want to use in cross-fold validation, and it takes the name of the metric as a string. So I'm going to run that. And then I'm going to take the square root of each of these scores. So here's what the scores it returns. It returns an array of 10 values. And I'm going to take the square root of these scores. And actually, it returns negative values. I'm actually not sure why it returns negative values. I actually don't know that. I don't know. Sanan, do you know why that is? Why it takes why the cross-val score returns negative values? Positive values would make more sense to me, but the cross-val score is returning these mean squared errors, actually, I'm not totally sure why that is. Then I take the square root of all these values, and then I take the average for my validation, mean squared error, which, as you can see, is slightly different than when I just did the train test split, as one would expect. So I know we went over cross-validation last class, but any questions about what's happening here behind the code?
Maybe just kind of a general question. I think most of us have done linear regression before. We've never split it to train and test data. We just run a model and we find the confidence interval or
Yep.
statistical significance of the parameters.
Yep.
So would you recommend doing a training and testing this way, or basing our decision on something like versus rows?
That's a really good question. I think you definitely can. I mean, I think it's valid. Both approaches are valid, and it comes down to, and I'll go over the confidence intervals in just a minute, some of the examples. But I think both approaches are valid. I think that the p-values, people can place sometimes too much faith in the p-values if they don't understand the underlying statistical theory. The p-values also depend on your model specification meeting the underlying assumptions of linear regression, which I think a lot of people don't grasp all the time as well. But I think they're both valid ways of doing things. The reason I like this is because it's a test of how well your model generalizes to out of sample data. But I would say they're complementary. They're not mutually exclusive. Yeah. I don't know, Sanaa, would you have anything to add to that?
I think it kind of depends. So there's two ways of looking at it. It's almost like what I was talking about earlier. Are you looking for just robust accuracy, or are you looking for robust, minimization of mean squared error? Is looking for the best model in the sense that it is predicting correctly? Then if you're going to go that route, then I recommend doing the train test split. But also, if you're looking at your p-values, your t-values, your t-statistics, things like that. We actually went over this when I was in San Francisco. This is the night they were doing this as well. We were going over the p-values and all that. And they were talking about, the problem is, just because it has a low p-value or a high p-value doesn't mean that it's a bad parameter. So you have to kind of take a grain of salt and look at the rest of the features and say, okay, well, how does it compare to the rest of them? So when I was saying, people place a lot of confidence in their p-values and things like that. It's not overconfidence. You just have to be aware of the problem domain. You can't just rely on, not making sense. I'm sorry. I feel like I'm right at this point. You just want to be aware of the problem domain, and just getting rid of variables just because of the p-value might not always be the best thing to do. You might even lead to an actual decrease in model evaluation.
Yeah. I think the p-values are really important, but if you think about what I have seen done, which I think is where the p-values can be abused, is if you think about a threshold cutoff of 0.05, which is a typical significance cutoff, what that essentially means is if you're running, let's say you run 100 models on average, and each time you're looking for this cutoff, on average 5 of those models, and each time it's significant, let's say, on average 5 of those models will be wrong, will be misleading, even if all of the other underlying assumptions are correct. And while that might sound like a little bit of a stretch, like running a model 100 times, I've seen crazy things in terms of people torturing data to find that one, needle in the haystack that may or may not really, that may actually be in fact illusory. But I'm not saying that to bash the inferential nature of it, and we'll get to that we'll get to cover that in just a moment, how you do that here. But
I've seen models where every single feature had a 0.2 p-value, but it was still predicting, good enough. It was still they were satisfied with the mean squared error, they were satisfied with the metrics. It's just that the p-values were above 2. So it's honestly, it depends on, you're looking for the statistically, you want to torture it enough to get the statistically the best thing possible, or are you satisfied with good metrics? Which is why the metrics generally is the route people choose to take, and if the metrics aren't improving, then you might want to turn to your p-values and say, okay, which of these can I get rid of to try to make my metrics better?
Yeah. Great. Well, we should move on. But so that's the syntax for cross-validation. Any questions about the cross-validation piece in addition to what Heather raised? Even anything about this at all? Yeah.
I just typed in, I was looking at help cross-val score.
Yeah.
And just to check out the first parameter
Mhm.
for the estimator is estimator implementing fit. Is there anything besides what we just learned in Nearest Neighbors that we should know that goes in there? Like what other?
Like right here where it says estimator?
Yeah.
Okay. Yeah, so the question was, what other inputs can be placed for the estimator in the cross-val score? The answer is it's really based off of almost everything we're going to do in the class. We'll have some kind of scoring function. Even the, actually, you know what, I'm not sure we would do this with the unsupervised, but for all the supervised models that we do in this class, linear regression, decision trees, random forests, everything we do here, logistic regression, KNN, there will be there'll be a metric that we use, and the scoring input here, which will be root mean squared error, it will be accuracy, it will be sensitivity, things like that, and then we'll have our estimator, which can vary. So that's one of the nice things about using scikit-learn is that the syntax is going to be the same. We're just swapping out whatever model we want to use, whatever scoring metric we want to use. But pretty much any supervised method in scikit-learn can be placed in this estimator argument. Yeah. Any other questions? Okay. All right. So now let's do another quick exercise. And I'm going to ask you to run a multiple regression with radio and TV this time, and look at which coefficient has the higher value, and calculate the 5-fold cross-validation root mean squared error, and compare it to the previous root mean squared error. So go ahead and do this again. You could do it by yourself, or you can do it in groups. All right, let's go ahead and get started again. So the exercise, the question was to do the same thing as before, except this time with 2 input variables, radio and TV spending, as opposed to just the one like we did before. And I saw a couple people get sort of tripped up on the syntax here, so I just want to take a moment to go over that. So basically, to do a multiple linear regression, here I'm giving it another name, just arbitrarily MLM, for my linear regression object. Then I'm going to run the fit method, and the inputs to the fit method, just as before, are the x and the y. First x, then y. So it's the same syntax from that perspective. Now, how do we get the x for a multiple linear regression? Well, I'm just passing the data frame, the trained data frame, which is subset by a list of strings that correspond to column names in my data frame. Say that again. Subsetting the data frame, passing the trained data frame, which is subset by a list of strings that correspond to column names in my data frame. Yep. Question was, what am I doing on the first line? MLM equals linear regression. I'm just creating a linear regression object. I'm instantiating a linear regression object. I haven't passed it any data. I haven't estimated any coefficients yet. I'm just saying I'm going to run the linear regression. And I'm associating that with MLM, which is just a name I define. Fit is the method that is going to estimate the parameters, estimate the beta values. Hmm? Yep. Any questions about that? John, I see you shaking your head back there. Any questions from you? Okay. All right, let me take a moment to digest that, and while you're digesting that, I'll go ahead and, for right now, I'll just put this in. I'll just put this in Slack so you guys can use it on your own code. Okay, so I've got that. Now I'm going to look at the coefficient values associated with both of my variables. You can look at the coefficient values. Just I need to run it first. You can look at the coefficient values just by typing in the name of the fitted regression, and it will spit out an array corresponding to beta 1 and beta 2 in this case. I'm actually going to create a little bit of code that will actually print out the name of the coefficient as well as the coefficient value using the zip, which in this case is taking two list objects and it's zipping them together. So it's putting the radio with the string radio with the first value and the string TV with the second value, and then it's just iterating through and printing out the first row and the second row. This sort of looks a little bit convoluted, but I'm just doing it to have a nice printed output, and you could use the same code to print out the results of your regression equations for your project, and all you need to change is the model that you're using to fit here. So I'll just go ahead and print that out. And you can see that the radio has a coefficient of 0.17, TV has a coefficient of 0.047. So based on this data, it appears that radio is more strongly correlated. Based on this based on what we know about the data so far, it appears radio is more correlated with sales than TV, although they both have a positive relationship, positive correlation with sales. And if you've done linear regression before in Excel or R or SAS or Stata or SPSS or whatever you've done it in, you'll always get you'll always get coefficient values, and you should get this exact same coefficient values regardless of what software you use. And you'll have more than this, but you won't have less than this. You will have these coefficient values that describe the direction of the relationship and the magnitude of the strength of the correlation. Okay? Any questions about this? What's that?
The error you got object as an attribute coefficient.
This one? Oh, so this is an error that I got because I didn't actually run. You see how I ran MLM equals linear regression? I didn't actually fit the data. I didn't estimate the coefficient. I didn't calculate. I didn't run through all the matrix algebra, and so it didn't have this attribute yet. So it gave me an error. It said, hey, I haven't calculated the coefficients yet. The zip is just for making the output prettifying the output. And zip is just taking this there's two elements in this list, and there's two elements in this array, and it's taking the first element and zipping them together, and the second element and zipping them together. Yeah. That's just a basic Python feature. Okay. Moving on. So now I'm going to calculate the cross-validation score, five-fold cross-validation score, just as before, except now with my multiple linear regression. See, I get 1.70 here. And going back to the previous one, I got 4.2. And this is a 10-fold cross validation here. Let's just make it 5, just to be fair. Same thing. 4.26 compared to 1.70. So it appears to be an improvement in our ability to fit the data.
Should we be getting the exact same, or you didn't see the equals 5? For the one we just did, the multiple regression?
You should get something very close, but you shouldn't get the exact same thing.
Oh, right, because it's randomly selecting.
Yeah. The cross validation, I didn't set a random seed in the script, and so you probably will get something slightly different.
Okay. What is the random? We did it at the top.
I didn't set a random seed in this script. A random.
If you can set it equal to one thing, so somebody else replicates that code.
Yeah. Yeah. Yep. All right. Any questions about that? Okay.
So, like, how would you graph that?
How would you graph this? Good question. So there's a couple different ways you could graph it. You could graph a 3-dimensional plot, and so you'd see a plane, which would represent the line of best fit, and that's one option. Another option would just be to have two scatter plots, sales and radio, sales and radio, sales and TV. And you have a line of best fit in both of those cases as well.
Can you like plot polynomial?
This isn't polynomial regression.
Or the
This is just linear regression.
that one's just
Yeah. Yeah. So you can also, and actually I'll show this in just a moment. You can also plot, a very common plot is plotting the residuals, plotting the error term over the range of predicted values. Plotting the error term over the range of x variables. Those are sort of diagnostic plots to assess how well your model is actually fitting the data. But the way I've done it, when I've done linear regression for like client work that I do, is I'll have multiple terms in my linear regression, and for like the executive briefing, maybe I'll take the one variable that I'm most interested in. That's maybe the most strongly correlated with whatever metric I have, and visualize that relationship, and then show the rest of the results in like a table or in the equation. Here are the beta values for the rest of the results. That's a good question though. What have you guys done? Those of you who have done linear regression, multiple linear regression, how have you presented that information to colleagues and clients and people you work with?
You need a tool set within Excel that allows you to take advantage of the pivot table. And what you do is, as it spits out your coefficients, it just puts them into an index, and I can select which coefficients I want to put in, and it changes my predicted value columns automatically.
Okay.
So, say in one analysis I have maybe 8 things I'm progressing against.
Mm-hmm.
And then I figure out which ones I don't like. Maybe the next one's 4,
Uh-huh.
the next one's 3, or something like that.
Yeah.
If you can think about those values being static, and then put into a table, I can select which column and then which I want to use as coefficients.
Okay.
And then they just,
Okay. Great.
I guess here, like, it's great when you have a complete data set. It's super simple to go straight through. But sometimes it's kind of like, I want to see what my data look like for just January and June or something.
Mm-hmm.
Like a month or whatever.
Mm-hmm.
It's just super fast.
Yeah. Yeah.
Like that.
Yeah.
Like I would use this all the time if I had data sets available. I have to fly, right? If I needed to do the data.
Yeah.
And then do this.
Yeah. Yeah.
I think it really depends on your audience and understanding them. So when economists speak to each other, it's a flat table that looks really boring.
Yeah.
That's got coefficients, and then that's enough. But how I've seen it broken down for economists that are like presenting it to say policymakers is just a quick bullet format. So like for a linear regression, you just take the coefficients and you just put it in the layman's terms. Like, you know, a 4% increase in radio sales or a dollar increase in radio sales will result in a radio spend, advertisement spending will result in an X amount in
Yeah.
yeah, it's a bullet format.
Yeah.
But otherwise, yeah, you really have to understand your audience. If they don't understand a linear regression, they won't even care about the formula or anything like that.
Yeah. Another way that I've seen this done, somebody on my project actually did this. They actually did a regression equation and then put their coefficients into Tableau. And then Tableau is just a dashboard, a commercial off-the-shelf solution dashboard, and they could select different sliders and drop downs, and based off those values, it would multiply all of the input, the X variables, by those values that were selected in the filters, and then you get a different, here's your baseline value based on everything, and here's where, when you change these filters and sliders, here's the resulting difference in your target variable. Yeah. That's a little bit more specific to using specific software, but that's something you could think about as well. Yeah.
Can you in Python do a 3D graph?
Yeah, you can.
Okay.
Yeah.
If you did split it up into two,
yeah.
Would that be the same as just a single linear regression, or with a single X variable and then another one with a single X variable, or is that getting the?
Good question. So, first of all, in terms of the syntax for doing what I just mentioned, we're going to be talking a lot more about plotting in like highly dimensional space in the next class when we talk about clustering. But in terms of your question about the regression line of best fit, will the line of best fit be the same? So let's say in this case, will the line of best fit for radio be the same in the multiple linear regression as in the previous linear regression? Well, so let's actually just look at it. So here you have we did the radio first. So this is 0.17 in this case, and in the previous case, it is, where did I go? It's actually just, I can just do this. I'm singular. 0.187. So it is different. And the reason for that, this is a really big thing, the reason for that is because these variables are not completely independent from one another. Which is a common sort of issue to run into when you're doing linear regression. Based on the functional form of linear regression, you're assuming that each variable is independent from each other. That's why they're called independent variables, because you're making the assumption they're independent from one another. And independently, they explain your dependent variable. But in reality, that's rarely ever the case. It's not a deal breaker, but it's something to be aware of. And there's lots of different ways that you can check for collinearity or multicollinearity, depending on who says it. But what you see is, in this case, some of the variation so in this case, there was some more variation that was attributed to this coefficient, versus this case, some of the variation was attributed to the other coefficient. So it was like it was almost swallowing up some of the variation from another coefficient.
Right. Yeah. No, that makes sense to me. That's why I was asking. If you graph it, if you were to display it on your display, it would be having beta be for, I guess, the first one is radio in your case.
I mean, I think that might be, I don't know. I think that would probably be a subjective choice. Which one you wanted to show? If you're showing a scatter plot, depending on what kind of point you were making, what kind of audience you had.
Line of it, yeah.
Yeah.
I mean, ideally you do it for you, but like if
Yeah, yeah. Good question. Good question. Won't be talking about collinearity too much in the class. I mean, we'll definitely can talk about it like offline. There's something called a correlation coefficient matrix, which you can use to check for collinearity. You can just look at a scatter grid, which we went over in class, and you can use that to check for multicollinearity. Actually, I will say something about collinearity towards in just a moment when we talk about variable transformations. But I'm sort of getting ahead of myself a little bit here. Any other questions about what we just did? Okay. So I wanted to go next to common transformations, common variable transformations that you will encounter when running linear regression. Now, there's a lot that could be said here. I'm going to talk about 3 of the most common variable transformations that I've seen in my experience applying linear regression. And to do this actually is right off of collinearity. So one of the things you might be interested in is not just the individual effects, also known as the main effects of a particular one variable relationship on the output variable, but the combined effect of 2 variables on the output variable. In statistical terms, this is known as an interaction term. In marketing terminology, or business tech terminology, this would be known as synergy. So what is the combined effect of 2 variables on another variable? And typically, this is something that you can use in response to variables that appear to be very correlated with each other. So in the example show here, I show how to create an interaction term between radio and TV. So if you look at the scatter plot and you see that radio and TV do indeed appear to be very correlated with each other, one way to address that in your model specification is to include an interaction term. So the interaction term here is just going to be the product of the radio, the radio amount and the TV amount. So the way that I'm going to do it here is just to create another column in my training set, call it radio TV, and then I'm going to multiply these 2 columns by each other. Fit a linear regression, call it LMI, linear model with intercept, and now I get 3 coefficients. And I get 2 coefficients for each of my main effects, and then 1 for my interaction effect. One note about using interactions is that, at least from what I've seen, convention is that when you include an interaction term, you also include the main effects as well. And so that's what you see here. Another common transformation. So before going to the next thing, any questions about interaction term? Have you guys heard of this term before? You guys have heard of this before? Yes? Getting some yeses? Okay. So this is something you can do in response to collinearity. Now, this is sort of what I would say is one of the downsides of using linear regression is that, or this approach to dealing with collinearity, is that you sort of have to manually know, either because you've seen the collinearity in the data or because you sort of suspect that it's really not just what I'm spending money on, but maybe it's what I'm spending money on and the region in which I'm spending it. That would be another example of the interaction term. So you sort of have to have this intuition or this hypothesis, and you have to manually specify what the interaction term is as an input before you even fit your linear regression. So I would say this is one of the downsides of using linear regression, and as we'll see when we cover decision trees and random forests 2 or 3 classes from now, one of the strengths of those techniques is that they automatically account for these interactions, these subtle interactions in the data, in a very specific way. We'll talk about that. But that is that is that. So another thing that you'll very commonly encounter is categorical variables. And linear regression can take categorical variables, but you want to, you need to do a transformation on these categorical variables so that it can be fed into this procedure that we've just gone over for estimating the coefficients. So to illustrate this process of the proper way of encoding categorical variables, let's say we have a variable in our data set, the major, and we're trying to predict earnings 5 years out of college. So our major, we have 4 different majors in this data set: computer science, engineering, business, and literature. How do we encode this for a linear regression? The answer is that we create k-1 binary dummy variables. This is the standard way of including categorical variables in a linear regression. And when I say categorical variables here, I'm specifically referring to categorical variables that are non-ordinal, meaning their order doesn't really have any significance. Okay, so non-ordinal meaning, agree, strongly agree, disagree, neutral, agree. That would be an ordinal categorical variable. You could possibly encode that as 1, 2, 3 if you wanted to in your data set. But specifically when you have a non-ordinal category, this is the way that you would encode it. And so you would have columns representing trues and falses for each category. Okay? Now, can anyone tell me why I would choose k-1 columns versus just k columns? Why do I have 3? In this example, I've got 4 different majors. Why do I only have 3 columns versus 4 columns? Yeah. Yeah. So what Jody said is you don't need the last one. It's redundant information. There's a lot of different answers you can give this, but that's probably the most intuitive explanation. You don't need to have all 4 variables. A very simple example of this is, let's say you're trying to predict the wages, same case as before, but instead of 4 categories, you have 2 categories, male and female. How many columns do you need to represent that information? 1. If you have 2 columns, that's going to be redundant information. So you only need 1 column, just 1 or 0. In the same way, you always are going to need 1 less column. Does that make sense? Yeah? Okay. So, another question. Does it matter which column you choose to leave out? Or is that irrelevant? 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 Okay. It's actually not irrelevant. It is very relevant because whenever you are evaluating the effect of a particular level, the coefficient associated with a particular level, that coefficient is not something that you just interpret in a vacuum. It's in reference to the base level. So if you got a beta value, engineering, 0.5, that's a positive relationship between being an engineer and 5-year earnings. But what is that in reference to? 0.5 more than what? 0? Like, that doesn't make sense. You don't have no major. You have to have a major. Which major is it in reference to? Well, in this case, it would be in reference to computer science. So the beta values for categorical true-false encoding like this is always in reference to the base level, the level that you leave out. Okay? Yes?
What if the K that you choose have to be all encompassing. So for example, like college majors, you would need a much larger list than that. Because if you omit some.
Yes, so in this case, this is just let's say there was a sample of data where you're just comparing the differences for these particular 4 majors. If you had more majors, you would need more columns. Okay. Is that what you were asking, or were you asking something more subtle?
I mean, I guess kind of. I mean, I'm just saying, like, you could group the majors into more general categories, but I mean, if you're not including, say, like, I don't know, art, they're in there.
Yeah.
That would show up in the error term, but wouldn't you, when you're creating these dummy categories, don't you want, like, all the possible values of college majors to make some kind of decision? Like, and then that becomes important when you're like defining your interaction term, doesn't it? Because then you would have noise.
So yes, you'd want to include all your majors. But the value for any given beta coefficient wouldn't be in reference to all of the majors. It would be in reference to the baseline major. And in this case, the baseline major is computer science.
Okay, but like, that's why you want the full set of majors. No?
I think the assumption here is that there are only 4 majors. Like, this is just a subset of data. It's not population. It's just saying if you take this that you go to college and you can only pick one of those 4, just for the purposes of this example, like 0, you need one of the 4, and that would be. But like, really,
Okay.
Mm-hmm. Yeah. You want to include all of the variables that would. So that's sort of gets to a slightly different question. How do you choose which variables to include in your linear model? Possibly. But I mean, if you have more people that fall inside these categories, then you need to have all of the categories that represent all of the people that you're trying to measure. All the people who went to University of Wisconsin. You should have a full list of majors for everyone who went to University of Wisconsin. Yeah. Yeah. Does that answer your question?
Yeah,
or?
I was a little bit cloudy there. But
Oh, okay. Okay. Yeah, we can talk about it more
okay.
after the class. Yeah. Okay. So, this is just a review of what I said. Going back to a point I made earlier, it's not the only way to encode categorical data. I think this would be a valid way of encoding categorical data if you have an ordinal set of categories, like strongly disagree to strongly agree. I think that could just be represented as 1, 2, 3, 4, 5 in a single column, and you wouldn't have to split it out. I don't know. Do any of you guys have any thoughts on encoding ordinal categorical data? Would this be the way that you would do it? I mean, I would say this would be the way I would do it. The assumption you're making here is that the difference between strongly disagree and disagree is the same as the difference between disagree and neutral, which is the same as the difference between neutral and agree, because that's the way you represent each one as a unit increase based on the previous one.
The difference does exist?
What's that?
You said the difference does exist?
Well, if you were to represent these 5 categories as 5 numbers, up by 1 unit, you're making the assumption, just by the nature of your specification, that each category is equally different from the previous category.
Well,
But
the way I understand it is that those 4 levels, there's nominal, ordinal, interval, and ratio.
Mhm.
At the ordinal level, there is order, but differences between them aren't consistent. So you could or you couldn't make the assumption that the differences between 2 and 1 is the same as 5 and 4.
Right. And I'm talking about for the ordinal.
Okay, so
For the
ordinal
ordinal.
difference means you can't assume the distance means anything.
So there's definitely an order here.
Yes.
And what I'm saying is, if I were doing a linear regression, I would just include this in one variable. 1, 2, 3, 4, 5.
Oh, yes.
I would do the categorical encoding before. Whereas the previous one was nominal, it was non-ordinal. There's no order. You know, I can make the argument engineering is better than computer science, but that's just subjective.
Okay, I misunderstood.
Oh no, that's fine.
I would do that.
Any other thoughts on that?
What if you didn't take it to be, you could have each one. We could have one column saying like what level of grade or whatever.
Yeah.
Right, and then each record could have one value, 1.5.
Yeah.
If you plug that into a regression, though, it would seem like going from strongly disagree to disagree and disagree
Yeah.
neutral
Yeah.
is just one.
Yeah.
Because you're multiplying that by
Mm-hmm.
whatever beta
Yeah.
is on that coefficient, right? So
Yeah.
it would be just doubling it or tripling it or multiplying it by 1.
Well, here's what here's what I would say about this. Whenever you have a beta coefficient, it's always, the plus or minus is not dependent on the scale of the input variable, but the interpretation of the magnitude of the impact of any given beta value, like any given input variable, is always going to be interpreted on the basis of what was the scale of my input variable. So a unit change. A unit change in this case will be going from strongly disagree to disagree, or neutral to agree. Whereas, a unit change in our example means spending an additional $1,000 on sales. So if you have two input variables, one is in thousands of dollars and one is in millions of dollars, you've got to be aware of that when you're comparing the two beta values together. So that would be people talk about centering and scaling the data. That can be a reason to make that kind of transformation, because you want to have a one-to-one comparison, but you could, as long as you're aware of the scale that's being used, you can use that to understand what the beta value is.
Right. If you got the beta value, though, say it's like 2, right?
Yeah.
And then that was predicted beta.
So let's say 2 is, 2 means, for someone who increases, their, for a unit increase in like how positively they respond to this question, that corresponds to, $2,000 extra for folks who do your bonus, for example.
Right, but then if you multiply that, so that would be multiplied by 2,000. So then if you multiply it by the next one, like you plug in a different value, would it just be that many? Would it be 6,000? I guess if you had neutral. If you were neutral.
Well, remember the beta value is just the slope.
Right.
It's not the absolute value. It's just the slope. So it's the measure of, for a unit increase in X, how much corresponding increase in Y.
So that would just
So if
be
you have,
divided.
and if you have, you want 2 units increase in X, and that, or, then you would just multiply it by 2.
So 1 unit increase here would be going from 1 to 2. Or
Yeah.
2 to 3.
Yeah.
Okay,
Yeah.
that
Yep.
And anybody can disagree with me. So where I work, we've done these kinds of surveys where we've used this kind of language, and we've asked these questions, the same question referring to a certain period of time, like their attitude toward a certain thing at a certain point in time. And then we said, okay, well the average, like say weighted score was like a 2, and then it increased to a 4.
Yeah.
And then as soon as we would talk about that change, like between disagree and say neutral, then we got, that's where a lot of debate was triggered. So, and that's what I think is like, when it's good to include these things in like an OLS regression, but I wouldn't go as far as to say that a unit increase would trigger X reaction. I would just use it as a justification that you fit a good model and you take into account to it. But as soon as we get into that discussion of like a 1 unit increase, then that's what people are going to get.
Sure. I mean, what you're, I think generally, if I could just generalize what you're saying, you've got to be careful about what linear regression does is attempt to measure a correlation between variables, and what I just basically said casually, which was a statement about a causal relationship. And causality is, as we all, I'm assuming if you're in this class, you know that correlation does not equal causation.
What?
There's a really funny website that shows how on the x-axis how the unit purchase of cheese in America correlates to the number of people that are strangled by their bed sheets over the same period of time. There's all sorts of crazy, spurious correlations out there, and if you look hard enough, you'll be able to find some for yourself. But that doesn't necessarily mean there's any real relationship there. So that's just a general word of caution.
It's posted my favorite correlation between Nicolas Cage movies and swimming pool drownings.
Yeah. Oh man, there's so many good ones. So many good ones. There's a difference between applying the linear regression and understanding the math behind the linear regression, the syntax behind the linear regression, and actually understanding the nature of their actual relationship. That's where experiments come in. That's where just understanding the domain you're in comes into play. Although even that can be contentious. I think this correlation is a causal relationship, and somebody else thinks otherwise.
Well, I'm saying you can say something about your coefficient here.
Mm-hmm.
And that's good.
Yeah.
But it's still, all I'm saying about this is specific to this kind of example is that you get into danger territory, I think, as soon as you start saying a 1 unit increase results in this. But it's good to say, it's good to point to the beta coefficient, and it's good to point to the fit that you produced using this. But
yeah.
But that's
Yeah, I buy that. I buy that for sure. Okay, so I'm going to switch back to the code and going to show you how to implement the dummy variable encoding that I just showed you. Pandas actually has a function called getDummies, and I'm going to use it here. The way it's applied is that you call getDummies, and then you specify the categorical variable you want, which here is the region variable. And I am going to, so first of all, let me just run this and show you what this returns. So previously, let me actually just show you the arrow.region counts. So here you see I have these 4 regions in my data set, and they're just in one column right now. And what I'm going to do is I'm going to turn that into a data frame of dummy variables, which you can see here. And so, because this data frame is sorted by regions currently, the first observation just have 1s in region 1 and then 0s in the other. And what I'm going to do is specify which columns I want to grab. And also, by default, specifying which columns I don't want to include. And so for this case, I'm going to set my region 1 equal to my baseline level. I'm just going to take 2, 3, and 4. And I'm going to do this with the iloc function. And I'm just saying all rows in my iloc function, and then 1, which is the second column, to the end. So when I run this, you see now that I just have the 3 columns. Region 2, 3, and 4. Any questions about that? So if you wanted to, you can use this syntax to control exactly which baseline level you want. Okay. So now I'm going to use the concatenate function to add these dummy variables back into my original data frame. And there they are. So I have the original region variable, which I've never gotten rid of, and then I've got the 2, 3, and 4, which I specify for my dummy variables. Any questions about this?
You want to explain line 141 again?
So line 141 is just taking this single column that's a categorical variable, and it's breaking it out into multiple columns. And then once it breaks it out into multiple columns, I am selecting, using the .iloc, I'm selecting all rows and 1 to the end columns. So it's leaving out the first column. Make sense? Okay. All right. So that is the using the dummy variables, and then you could go ahead and you could place, just like we did the multiple linear regression before. You would specify, region 1, 2, or region 2, 3, 4 in your regression equation. I'm not going to do that in this example, but it's the same way as we just did for the multiple linear regression.
How would you use that? I get you split it into 2, 3, 4.
Mm-hmm.
What placeholders
Mm-hmm.
or predicted ones?
Yes.
Basically, would say from this data which region you would fall into.
You would actually the opposite of that. You based on this region, what is the impact of this particular region on sales? On sales, your target, your response variable. Yep. So if I ran a regression, I would get beta values associated with each of these categories.
But not interlinked.
What's that?
But not interlinked. Or is it?
I would get a beta value associated with this, beta value associated with this, beta value associated with this. Okay, I'll do it real quick. Actually, you know what? I'll do it after class if you want to see it. I've got 30 minutes here. Gonna try to run through a couple more things. The last common variable transformation that I wanted to go over is the log transform. Specifically, the log linear model. Okay? Also known as the log level model. How many of you guys have implemented a log level model before? Log linear model? 2? So, in what cases would you implement a log linear model? Or any ideas? Okay. So, there's a couple of different reasons why you might use a log linear model, but this sort of gets to the assumptions that the linear regression is based off of. Okay, I included a link to this article that I thought was one of the most helpful articles I read about the assumptions of linear regression, and it talks about 4 assumptions of linear regression: one being linearity, one being independence of errors, specifically over time. Another being something called homoscedasticity, which just means constant variance of the errors over time. And then lastly, the normality of the error distribution. So the linear regression, so this is a lot of, what is all this? I'm not going to go over all this time. Maybe if we had another class, I could go into this, but the linear regression does not assume that your input data, that it does not assume that your output variable is necessarily linear. Okay? What it does assume is that the error distribution of your linear regression is, it doesn't assume the input, the response variable is normally distributed, but it does assume the error distribution is normally distributed. And what does that mean? Well, what it means is that, let's see here. What it means is that if you have a simple linear regression, you've got your x and your y here. Let's see if I can draw this. It assumes that for any given point on your x, remember horrible drawing distributions here, you have a normal distribution of your errors across the range for a given x value. So let's say this is age. This is the height of a person, height, and then age. It doesn't assume that height is normally distributed, which it generally is. What it instead assumes is that for a given age, for young children versus for teenagers versus for adults, let's say 30, 20, and 10. For 10-year-olds, height is normally distributed. For 20-year-olds, height is normally distributed, et cetera, et cetera. And so that's not always the case in data. Like the data doesn't always have that normal distribution. So one of the things you can do about it, and I'm sort of getting ahead of myself a little bit here, but it also assumes that the constant variance of errors is also very similarly related to this. It assumes that the errors here are very similar, are similar in terms of their spread here as the errors here. So this kind of thing here, that would be non-constant variance of errors, because the variance of the errors here is much higher than the variance of the errors down here. Okay. Why am I pulling all this abstract math out of left field right now? Well, because it's in this context that some of these variable transformations have their relevance. Okay? If you would like to learn more about, the inferential nature of linear regression and these assumptions that linear regression is based off of, this article is a great starting place. We could also talk about it in office hours. Unfortunately, we're not going to have a ton of time to go into it right now, but I did want to show you the syntax. For those of you who are already aware of it or are in the process of learning it, I wanted to show you the syntax in Python for the log transform, which I have used the log transform to counteract some of these assumptions being violated, specifically when I have non-constant variance over time. Yes?
So when you have the non-constant variance over time, heteroscedasticity, then you can still fit a good model. You can still draw a pretty good fitted line.
Yeah.
But then what you say about the beta is it can be, like, if I remember this right from like a long time ago, then the value that you have of beta and the certainty that you have associated with that beta is, you might get the value of beta right, but the certainty that you have about beta's value being what it is, that's the problem, right?
Yep.
Okay.
Yeah, no, that's a great point, Bennett. And I would just like to draw out what Bennett just said. Maybe I'll draw it over here. Is it okay if I erase this now? Sorry.
If you're curious, I already digitized it and put it on the GitHub main page, so.
Oh, that's right. So if you have a bunch of data, that sort of has this funnel shape, and your line of best fit, we'll get to line of best fit in just a second. Here's X and Y, age, height, for example. What this corresponds to non-constant variance over the range of your predicted values. This is known as heteroscedasticity. You know, it's a mouthful. Heteroscedasticity. Non-constant variance across time. Homoscedasticity is when you have constant variance across time, or constant variance across your range of predicted values or your variables or whatever the case is. Now, what Bennett was saying is that you can still do the linear regression, get a line of best fit, and derive a beta value. Remember, you just beta the slope of the line. But what you lose when you have heteroscedasticity is you lose the confidence that your relationship, what the exact nature of that relationship is. And you can think about it on a conceptual level, just you don't really know if the relationship is like this, it's like this, it's like this. And the reason why is because the hypothesis testing that occurs when you see the p-values, I'll just go through it right now. The hypothesis testing that occurs when you have the p-values is based off of something called the standard error. Okay? And the hypothesis testing tells you whether you have a relationship or you don't have a relationship. The null hypothesis is that there is no relationship. There is no relationship between age and height. Another way of saying it is h null is equal to beta 1 is equal to 0. The alternative hypothesis is that beta 1 is not equal to 0. But when you have this, you don't have the confidence that comes from using the standard error to test your hypotheses that you would have otherwise. Because the standard error is the variance in the error. There are lots of ways to correct for this. There could be like an entire 3-hour class easily just devoted to heteroscedasticity. Kid you not. So I'm just sort of trying to give a little bit of context that if this is like way over your head and you're just starting to mind eyes glaze over right now, that's okay. I'm going to reel it back into a practical level. But if you want to talk more about heteroscedasticity, ways to deal with it, besides just this one method that I'm going to show you, definitely feel free and talk to me about that. And this article provides some additional context as well. So don't expect you to follow all that if you don't have that background. But if somebody asks you what is heteroscedasticity, which is a question I have asked data scientists that are trying to interview to come on my team, then you can say, I know what it is, or I've heard of it before. And I can go look it up and I can tell you. But that's a question that I just ask people out of the blue just to see if like they've heard of it before. Because it's a very common occurrence in when doing linear regression. So one way to deal with one popular way of specifying the linear model is to use a log linear model, and this just means that you take a logarithmic transformation of the response variable. And so I'm going to demonstrate that right now. First of all, I'll show you what I just showed you on the board, but in our own data set. And let me try that again. So here's a plot that you could generate to evaluate how well some of these assumptions, and again, I'm not going into depth on these assumptions right now, but this is a common diagnostic plot where you show the residuals, the errors for each data point in your data set across the range of predictions that you're making. And so you can there's not a ton of data points here, but you can sort of see the variance in the errors here appears to be less than the variance in the errors over here. So this is an example of heteroscedasticity on our own data set. So one way to deal with this is to take a log transformation of your response data. And there are other reasons why you would take a log transformation of your response data, but here I'm going to do the same model as before, except I'm going to take the log, and this is the log base E, but it doesn't really matter which base you use, log base E of the sales, a response variable. And I'm going to get a coefficient, which is 0.00385. So how to interpret a coefficient? So the coefficient for the linear model was a unit change in x, the corresponding unit change in y for a unit change in x. So when you have a log linear model, it's a little bit more subtle, but there's a very handy way of interpreting it. I just wrote it in the comments here. For a unit change in x, the beta coefficient corresponds to the percentage change in y. The beta coefficient for a log lin model, also known as a log level model, corresponds to the percent change in y. And this holds true for a unit change in x, but it does not hold true for outside of a unit change in x. Just for a unit change in x, for small changes. So here I've got my coefficient. I'm going to multiply it by 100. to get the percent. So I have 0.38%. That's what my coefficient is, 0.38%. So when I change x by a unit, what is the corresponding change, percentage change in y? Well, let's actually just go ahead and do it. So I'm going to run the predict. I'm going to predict on 30. I'm going to predict on 29. I'm going to predict on 30. And then I'm going to divide through by 29. So this is the change in y values, the percentage change in y, corresponding to a unit change in x. Percentage change in y corresponding to a unit change in x. And I'm going to multiply that by 100. And so you get almost the same thing. So this is an approximation. But this is the interpretation. And if you're thinking, scratching your head right now and thinking to yourself, why in the heck are we going over a log linear model? I don't know when I would use this. Maybe you never will. But this is a very, very common model used in, and for those of you who are economists in the room, correct me if I'm wrong, I think this is a very common model used in econometrics. Yeah. So it's handy to know. There's also, along with log linear model, there's a linear log model, and there's a log-log model, each with their own interpretations, coefficients. I just included the one right now.
Linear log is the same as Poisson, right?
Linear log is the same as Poisson. I don't know. I don't know. I'll have to look at that and get back to you. Good question. One other thing to say about the logarithmic transformation, you would only use it if all of your response variables were positive. It wouldn't work if you had negative response variables, just because of the logarithm. Okay, so we should wrap up here. I included some more information in the presentation. Since we only have 12 minutes left, I think you'll get more value out of going over some code examples. I wanted to just show you code from stats models, which is a popular package in Python for doing linear modeling. And this package is nice because it shows like all these nice features that you probably are accustomed to if you've done linear regression in the past, and it gives you this interpretability back into your linear modeling. If that's an important part of your project, I would highly recommend looking at this. So the formula is the syntax for using the stats models is a little bit different. There's two different stats models you can use, one with the formula API, one without. I'm showing the formula API here because it's the most different. But basically, the way it reads is that you fit a linear model by specifying the formula or the model specification in a string format, where the tilde differentiates between the y variable and the x variables, and the plus signs don't indicate adding variables together, but they indicate the individual explanatory variables you want to include in your model. So if you are coming at this from an R background, as I was, this was really useful for me because it made a lot of sense to me. I know there's some struggles with selecting multiple columns. This is, they should give you the exact same results in terms of the coefficients. It just looks a little bit different, and it adds some additional features sort of built in. So I'll just run through these real quick. Here I'm fitting the linear model on 3 explanatory variables. Here I'm showing what the beta values are. Here I'm showing the confidence interval associated with each beta value. The confidence interval is based off of the standard error, and this is based off of this assumption that we have a normal distribution of errors. I'm not going into a lot of the statistics here. If you're interested in learning more about these statistics, come speak to me. I'm happy to talk to you about them. Here are the corresponding p-values. Here is just a summary method, which gives you a lot of information you might be accustomed to seeing this is very similar to like the R summary output. You see things like the coefficient values, the standard errors, which I've referenced, the t-values, the p-values, the confidence intervals. You also see some model fit diagnostics. We didn't really cover the R-squared value. I think if you've done linear regression, you probably are familiar with R-squared. The F statistic, which shows you, which tests all of your hypotheses, all of your relationships at the same time, and some other diagnostics as well. So feel free to use this if you'd like to, if this is an important part of your project. You're welcome to just take that and copy and paste that. I'll just briefly say, doing some of these variable transformations can be built in to the formula API itself. And here's some examples. Here's how you would include an interaction term. Excuse me. Here's how you would include an interaction term with the main effects. So it's just the asterisk. It means interact. And you see that it includes the radio newspaper interaction with the main effects. Here, the next example shows the categorical variable encoding that we talked about earlier. And it shows the, here you see the coefficients associated with the categorical variables that, not surprisingly, they're not significant based on what we saw earlier. And then lastly, if you want to do a log linear model, you can specify that with the function you want to transfer. And you could do this any custom defined function. It doesn't just have to be this particular function, but you can just include the function within your formula interface. Yes.
Let's just assume that this was a category for a second.
Mm-hmm.
When you look at your results your statistical results from the top of that,
Yeah.
what would you be heavily weighting? Would you be looking at standard error against R squared as sort of the be all end all? Or let's say that's bad.
Yeah. Yeah.
What's your next step in optimization? What would be your next step of focus?
Yeah, that's a really good question. There's a lot of different things you could do. One approach would just be to run this regression analysis and see which variables are significant, and then run the model again, for the category competition, but only including the ones that are significant. There's a lot more that can be done besides that. But that could be one approach to take. Visualizing your data, trying to understand the interrelationships and the subtleties, the interplays between the data, and then including those interaction terms can be part of it. Doing some of these model diagnostics and looking at the results of that and trying to transform the variables in different ways could be part of it.
And so as you're doing that, your judge, what's your output value that you're using to say that I'm increasing my accuracy or decreasing?
That would be based on the Kaggle competition. A lot of the Kaggle competitions use actually, I've never done a Kaggle competition with a continuous response. I'm thinking they're probably going to use a root mean squared error or some subtle variant of it. You saw Barry's example. It was the log likelihood function, which is like a subtle variant. It's a lot of times they use the AUC for the classification and the root mean squared error for the prediction, and you don't see that on here. At least I don't think you do.
So in this case, though, let's say linear regression was the method they wanted you to use.
Yeah.
What are you looking at? What's your number?
So you wouldn't. I wouldn't look at this R-squared value. What I instead would do is evaluate the model on the test set, because this R-squared value is based off of the data you use to actually train the model. If you really wanted to get an R-squared value, you could, be my guest, you could calculate the R-squared value on the out-of-sample data. R-squared is a complementary metric to root mean squared error. They're both metrics of the value. The F statistic is another one you could use, to compare different models with each other. Root mean squared error, I think, is the one that's really common. I think it's probably the one commonly used. And you could say it.
In my competition,
Root mean squared error. Okay.
Yeah, which is
okay.
a continuous
Yeah.
response variable.
Okay.
Actually, it's the root mean squared log error.
Okay.
Subvariable.
Yeah, just a subtle variant of it. So I'm just going to point you to what I included for you guys as a bonus. I created code to actually do what we did to write your own regression equation, just based off of like matrix algebra. And I included a toy example here, where you have your x variable, just this matrix, and this y variable is a matrix, and you calculate your own coefficients. And I'll just run this real quick so you can see. You can see that here's the one that I calculated just by scratch, just matrices, not negative 97, negative 328, negative 97, negative 328. Same thing. It's just matrix algebra. It's relatively straightforward matrix algebra. And here's using the stats. And here's the same thing with scikit-learn. They're all doing the same thing, at its essence. And if you want to program your own, you can. And when you get into higher, more complicated linear regression modeling techniques, you probably will want to create your own. You don't want it to just be a black box. You want to understand it. And sometimes programming it out can help you understand, what you're actually doing. I heard one of my buddies, who's a economist, said that one of the biggest criticisms that statisticians get is that they don't understand enough matrix algebra. And that's the criticism they'll get from the computer scientists. And I think it's really, I find it to be valuable to learn the matrix algebra, because then you understand what's happening. So if you want to play around with that, here's an example where I get the same results as we just derived using the matrix algebra for the advertising data set. Again, not totally optional if you're curious about it. So in conclusion, I just wanted to go back to our GitHub repository, make a couple of announcements, then we'll be done. And basically, no homework assignment this week. Just continue to develop your project. If you've got questions about it, if you've got questions about should I try harder in the path I'm going down, or should I pivot and do something different, come talk to us about it if you'd like to. We're happy to give you guys feedback. I know Sinan, are you having office hours after class today?
Yeah.
Sinana's having office hours at class today. I'm having office hours at 5 to 7 as per the usual. If you're interested in learning more about the statistics, the assumptions, the inferential aspects of linear regression, please come talk to us. I'm more than happy to talk about this. I also point you to 2 excellent resources, one of which is a free textbook called The Introduction to Statistical Learning, which is written by 2 professors from Stanford, and it has got hands down some of the best conceptual descriptions of the stuff we go over in class, any textbook I've ever read. They also have companion videos that highlight the key points that you can check out that are helpfully indexed on this link there. Here's an index of all the YouTube videos that correspond to the key points made in the textbook. And lastly, I found a really useful article that I've come back to several times, written by a professor at Duke University, that goes over in a very conceptual and thorough, and I would say practical way, the assumptions of the linear regression, how to test that they're being met, how to fix when the assumptions are not being met. And so if you want to go anywhere else to learn more about that aspect of what we talked about, I highly recommend these resources. So that's all that I had. Sinan, did you have anything else?
So that tree that I drew on the board, I made a digital copy and put it on the GitHub repo real quick just to show.
Yep.
It's on the main page on the README. It's like the 3rd link down, and it's just kind of like a digitalization of that tree. As we go through the class, I'll keep adding to it. So as of now, you'll see 3 models that you now know: logistic regression, KNN, and linear regression. So as we go forward, more, and so next week, this part of the tree will be folded a little bit too. As far as next week is concerned, I can go back to this. Sorry. So next week, we have a very interesting exercise. So you'll see data problem, clustering, and visualization. So clustering and visualization will be our first look at unsupervised models. Data problem will be something interesting. So this is actually the third time we've done something like this, and this is the second time we've used this specific problem. So what I have essentially done, so if I haven't mentioned this before, I apologize. I own a data science consulting firm. So one of my clients, previous clients, we did the problem of can we predict forward stock returns based on Twitter sentiment. So if people tweeting about Apple or Tesla, could we actually predict if Tesla or Apple would go up or down, and by how much? So what I did was I asked my client, he said fine, as long as it's protect the anonymity. So I changed the company name, I changed some of the dates and times, things like that, and which tenure. So next week, what I'm going to be doing is I'm pretending to be the CEO of a company, and I'm going to give to my team of data scientists, to be broken up into groups of 2 or 3, and I'm going to give you the data set and a 2-page write-up of what I want you to do with it. And you're going to be able to, you're going to have to somehow predict forward stock returns by the end of the 3-hour period of the data problem. So we'll do a brief intro to rapid prototyping and to what types of questions there's going to be, and I'll go over some hints and how other people solved it and things like that. But next week it'll be very interesting. It'll be very fun. It'll be very fun. And I'll put it this way. People actually achieved I would say pretty good results using one of the 3 models that we've already learned in this class. And actually, they need more by the time we did it last time. So you guys actually have it a little easier because you have less to choose from with which model you want to use. And with that,
All right.
have a great rest of the weekend.
Thank you.